Tonight, we're going to talk about distance, real distance. The kind that starts with Earth and keeps expanding, step by step, until the numbers stop feeling like numbers and start feeling like something else entirely. The kind where every step out is bigger than the last, and none of them prepare you for the next one. We're going all the way out to Andromeda, a galaxy 2.5 million light-years away that is moving toward us right now, and that no machine we could ever build would reach before it reaches us first. By the end of tonight, you're going to see exactly what that distance looks like at every step, what fills the void between here and there, and what happens to everything you know when Andromeda and our own galaxy finally collide. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what you already know. You are standing on a planet. That planet has a diameter of about 7,918 miles. From where you are standing, from any perspective available to human experience, this is enormous. A drive across the United States covers roughly 2,800 miles, and that takes days. There are mountain ranges on this planet so large that entire weather systems form around them. There are oceans so deep that the deepest point in the Mariana Trench descends nearly 7 miles below the surface. From your perspective, Earth is essentially boundless. You could spend an entire human lifetime exploring it and never see all of it. Now, pull back. The Moon sits about 239,000 miles away. It has a diameter of about 2,160 miles, roughly 1/4 of Earth's. Light takes just over 1 second to cross that gap. The Apollo astronauts needed about 3 days to do it. 3 days of continuous travel to reach the nearest thing in the night sky. That journey, completed 6 times between 1969 and 1972, remains the farthest any human being has ever traveled from home. More than 50 years have passed since the last time anyone went that far. Now step back further. The Sun is about 93 million miles away. Its diameter is roughly 864,000 miles. You could line up about 109 Earths across the face of the Sun. By volume, you could fit roughly 1,300,000 Earths inside it. Light leaves the Sun's surface and takes 8 minutes and 20 seconds to reach you. When you look at the Sun, you are not seeing it as it is right now. You are seeing it as it was 8 minutes ago. The image in the sky is already history by the time it reaches your eye. That delay seems insignificant at the scale of Earth and Sun. At cosmic scales, it becomes everything. The same light that takes 8 minutes to reach us from the Sun takes about 43 minutes to reach Jupiter. Jupiter, the largest planet in the solar system, orbits the Sun at about 483 million miles out. A planet so massive, you could fit 1,300 Earths inside it by volume. With a storm called the Great Red Spot that has been raging for at least 300 years. And that same storm is so small relative to the scale of the solar system that Jupiter itself is barely a point of light from Earth. Saturn orbits further out, still, at about 886 million miles, with its rings spanning roughly 170,000 miles, tip to tip. Light from the Sun reaches Saturn in about 79 minutes. When the Cassini spacecraft arrived at Saturn in 2004, after a 7-year journey, the radio signals it sent back to Earth traveled at the speed of light and still took over an hour to arrive. An hour at the speed of light, just to cross from one planet to a mission control room on another. Step back further still. The farthest planet, Neptune, orbits at about 2,795,000,000 miles from the Sun. Light from the Sun takes roughly 4 hours to reach it. Voyager 2, launched in 1977 and the only spacecraft ever to visit Neptune, took 12 years of continuous flight to get there. 12 years. And Neptune is still inside our solar system. Beyond Neptune lies the Kuiper Belt, a vast ring of icy objects extending out to about 4,600,000,000 miles from the Sun. Pluto lives here. So do thousands of other small frozen bodies, the leftover debris from the formation of the outer solar system. Beyond the Kuiper Belt, the Sun's solar wind continues to push outward until it finally meets the interstellar medium and gives way. That boundary, called the heliopause, is where the Sun's influence ends in terms of its wind. Voyager 1 crossed it in 2012, after 35 years of travel, becoming the first human-made object to enter interstellar space. But the Sun's gravitational reach extends much farther than its wind. Far beyond the heliopause, stretching out to perhaps 100,000 times the Earth-Sun distance, is the Oort cloud. It is a theoretical shell of frozen bodies that has never been directly observed, but whose existence is inferred from the long-period comets that occasionally fall inward toward the Sun. These comets arrive from so far out that their orbital periods can be thousands of years long. The Oort cloud's outer edge sits at roughly 9 trillion miles from the Sun. 9 trillion miles is just the edge of our Sun's neighborhood. Consider what it would take to cross it. At Voyager 1's speed, reaching the outer Oort cloud would take approximately 28,000 years. The entire span of recognizable human civilization, from the first cities in Mesopotamia to right now, is roughly 5,000 to 6,000 years. Getting to the outer edge of our own solar system would take about 5 times that. And the Oort cloud is not the destination. It is just the boundary, the place where our Sun's gravity finally releases its loosest grip on the material that formed with it. Beyond it, you are in the space between stars. The nearest star to our Sun is Proxima Centauri, about 25 trillion miles away. At the speed of Voyager 1, currently moving at approximately 38,000 miles per hour, the journey to Proxima Centauri would take about 75,000 years. 75,000 years to reach the nearest star. And then, beyond Proxima Centauri, Barnard's star at 6 light-years, Wolf 359 at about 7.8 light-years, Sirius, the brightest star in our night sky, at 8.6 light-years. Each of these separated from the next by distances that make the Earth-Moon gap look trivially small. Think about what that actually means for a moment. The Moon is 239,000 miles away, and reaching it took 3 days. The Sun is 93 million miles away, and light takes 8 minutes to cross it. Neptune is nearly 3 billion miles away, and Voyager 2 needed 12 years to get there. Proxima Centauri. The next thing after Neptune, after the Kuiper Belt, after the entire solar system, is 25 trillion miles. Not 30 billion. Not 300 billion. 25 trillion miles for the nearest star. And then Barnard's star is another 10 trillion miles further out from that. And Sirius, a star so bright it can cast faint shadows on a clear night, is about 50 trillion miles away. None of these stars are going anywhere particular. They are all part of the same slow orbital dance, each one moving at its own velocity around the galactic center, so gradually that on any human timescale, their positions in the sky appear fixed. Each one is a sun. Many of them have planets. Some of those planets almost certainly orbit in regions where liquid water is possible. We have detected planets around several of these nearby stars, including around Proxima Centauri, where Proxima b sits in what may be the habitable zone. But none of that proximity means anything in terms of travel. The nearest potentially habitable world beyond our own solar system is 25 trillion miles away, and at our fastest sustained speed, we could reach it in 75,000 years. Human civilization, in its entirety, is about 12,000 years old. Every star you see tonight is an isolation. Every point of light in the sky represents something separated from everything else by a void so profound that no living thing has ever crossed it in any direction. And all of these isolated stars, these points of light, separated by trillions of miles of nothing, all of them together are part of something. Every single one of them. Every star visible in the night sky. Every point of light you will ever see without a telescope. All of them are part of the same enormous structure, the Milky Way. We tend to picture the Milky Way as a flat disk, something like a vinyl record, simple in shape and familiar in outline. The truth is more complex. The Milky Way is a barred spiral galaxy. That means its center is not a simple point, but a bar of stars running through the nucleus, roughly 27,000 light-years long. From the ends of that bar, 4 major spiral arms curve outward. The Perseus arm, the Sagittarius arm, the Centaurus arm, the Norma arm. Between the major arms lie narrower secondary features, spurs and bridges of stellar material. Our Sun sits in one of those secondary features, a structure called the Orion arm or the Orion spur, bridging the gap between the Perseus and Sagittarius arms. We are not in a major arm. We are not at the center. We sit about 26,000 light-years from the galactic center in the outer third of the disk. 26,000 light-years. That is the distance light covers in 26,000 years, traveling at 186,000 miles per second. Light that left the galactic center when our species was still in its earliest stages of development is only now, today, arriving at the Earth. And we sit in the outer third of the disk. The disk itself spans roughly 100,000 to 120,000 light-years across. Some observations suggest stellar material associated with the Milky Way may extend even further in certain directions, with the outer disk warped and flared at the edges, like a hat brim that has been bent. The main disk is relatively thin in proportion to its width. The region where most stars are concentrated is only about 1,000 to 2,000 light-years thick. Enormous in absolute terms. Thin as a coin when you compare thickness to diameter. But the Milky Way is more than just the disk. Above and below the main disk sits the thick disk, an older population of stars, more dispersed in height, puffed up above and below the midplane. And surrounding everything, extending far beyond the visible disk, is the stellar halo. The stellar halo is a roughly spherical cloud of ancient, metal-poor stars and globular clusters. It stretches out to perhaps 100,000 to 300,000 light-years from the galactic center in all directions. A diffuse sphere of old stars orbiting on long looping paths that carry them high above the plane and back again. Globular clusters are remarkable objects. They are tightly packed, roughly spherical collections of stars, typically containing tens of thousands to several million individual stars packed into a region only 100 or 200 light-years across. The Milky Way has about 150 known globular clusters. They are among the oldest objects in the galaxy. Most of them formed in the first billion years after the Milky Way assembled, in the earliest epoch of galaxy formation in the universe. When you observe a globular cluster, you are seeing stars that have been burning for 10 to 13 billion years. The most massive globular cluster associated with the Milky Way is Omega Centauri. It contains about 10 million stars compressed into a region roughly 150 light-years across. Omega Centauri has multiple stellar populations with different chemical compositions, which suggests it is not a standard globular cluster, but the stripped-down core of a small galaxy that the Milky Way absorbed billions of years ago. It is one of many smaller systems our galaxy has consumed over its lifetime. The Sagittarius dwarf spheroidal galaxy is another. The Milky Way has been pulling it apart for billions of years. A long ribbon of stars, called the Sagittarius Stream, now arcs around the galaxy as a debris field, a tidal trail of stars scattered across a band millions of light-years in extent. Our galaxy grows by consuming its neighbors. The star count of the Milky Way sits somewhere between 200 billion and 400 billion. The range is wide because we cannot see the entire galaxy from within. We are embedded in the disk, looking outward through layers of gas and dust that block visible light. This is a fundamental constraint on what we can know. If you want to understand the shape of the room you are sitting in, you need to either step outside and look at it from a distance, or measure your way around every wall from inside. We cannot step outside the Milky Way. The nearest point from which we could look back and see the whole galaxy would require traveling to a dwarf companion galaxy in the halo. And the nearest of those is roughly 60,000 light-years away. So, we do the other thing. We measure. Radio telescopes map the distribution of hydrogen gas, which extends throughout the disk and is not blocked by dust the way visible light is. Infrared telescopes, launched into space to avoid the blurring effect of Earth's atmosphere, can penetrate the dust clouds and reveal star-forming regions and stellar populations hidden behind them. Gamma-ray and X-ray observatories detect the high-energy emissions from compact objects and explosive events throughout the galaxy. Systematic surveys of stellar positions and velocities, programs like the European Space Agency's Gaia mission, have measured the positions and motions of more than 1 billion stars with extraordinary precision, building up a three-dimensional map of our stellar neighborhood that extends outward for thousands of light-years. By combining all of these approaches, the picture that has emerged over the last several decades is one of extraordinary complexity and scale. The inner regions of the galaxy, particularly around the galactic center, are almost completely hidden in visible wavelengths. To study them, astronomers use infrared light, radio waves, and high-energy radiation, which penetrate the dust. The picture these wavelengths reveal is not simple. The disk contains enormous molecular clouds, regions of cold, dense gas where new stars are forming. These clouds can contain millions of solar masses of gas compressed into regions a few dozen to a few hundred light-years across. They are dark, invisible light, opaque, hidden by their own density. But in infrared, radio, and millimeter wavelengths, they glow with the emission of molecules, and the heat generated as material falls inward toward new stars forming at their centers. The Orion Nebula, visible to the naked eye, as a faint smudge below Orion's belt, is the near edge of a vast molecular cloud complex that fills much of that region of sky. It is one of the most active star-forming regions near the Sun, but it is small compared to the dense clouds near the galactic center, some of which contain tens of millions of solar masses and are forming stars at rates far higher than anywhere in the Sun's neighborhood. The spiral arms are lit up by hot young stars, blue giants that live for only a few million years before exhausting their fuel. These massive stars, some with masses 10 to 100 times the Sun, burn so intensely that they illuminate the gas clouds around them, producing the glowing nebulae visible in images of other galaxies as bright spots along the spiral arms. Our Sun, a modest yellow dwarf, is typical of the older stellar population between the arms, middle-aged, long-lived. Neither the hottest, nor the coolest, nor the most massive. Almost certainly not the first star to ever orbit in this region of the galaxy, and not the last. The spaces between the arms are populated by older, cooler stars on more circular orbits. And threaded throughout all of this, invisible but gravitationally dominant, is dark matter. Dark matter cannot be directly observed. It does not emit, absorb, or reflect light. But it exerts gravity, and by studying how stars and gas orbit the galactic center at different distances, astronomers can infer how much dark matter must be present and where it must be concentrated. The result is striking. Stars at large distances from the galactic center orbit at roughly the same speed as stars much closer in. This is not what you would expect if the visible mass of the galaxy were all that was there. It tells you that there is far more mass at large radii than the visible stars and gas account for. That extra mass is the dark matter halo. It surrounds the entire visible Milky Way in an enormous sphere, extending perhaps 300 to 500,000 light-years from the center. It contains roughly 5 to 6 times as much mass as all the visible stars and gas combined. The dark matter halo is the gravitational backbone of the galaxy. Without it, the galaxy as we know it would not exist. And deep inside all of this, at the rotational center of the disk, hidden behind a curtain of gas and dust 26,000 light-years away, sits something we know in extraordinary detail, despite being unable to see it in visible light. Sagittarius A, the supermassive black hole at the center of the Milky Way. Sagittarius A has a mass of approximately 4 million solar masses, 4 million times the mass of our Sun, compressed into a region smaller than the distance between Earth and the Sun. We know it is there because of the stars orbiting it. For decades, astronomers have used infrared telescopes to track individual stars in the dense stellar cluster surrounding the galactic center. They have watched these stars trace complete elliptical orbits around a single invisible point. And the only possible explanation for the speeds and shapes of those orbits is a concentrated mass of 4 million solar masses. The star designated S2 completes one full orbit in about 15.9 years. At its closest approach to Sagittarius A, S2 reaches speeds of approximately 5,000 miles per second. 5,000 miles every second. That is roughly 2.7% of the speed of light. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A itself. An image of the black hole's shadow, a dark region surrounded by a glowing ring of superheated plasma, visible at radio wavelengths that can penetrate the dust clouds. To produce this image, astronomers effectively turned Earth into a planet-sized radio telescope. They linked 8 radio observatories across 5 continents, separated by thousands of miles, and combined their observations through a technique called very long baseline interferometry. The resulting angular resolution was sharp enough to image a golf ball on the Moon. Even with that extraordinary resolving power, Sagittarius A appeared as a ring only about 50 micro-arcseconds across. That is how small our galaxy's central black hole appears, even to the best instruments we have, from our vantage point 26,000 light-years away. The image confirmed what the stellar orbit measurements had already demonstrated beyond reasonable doubt. The mass is real. The concentration is real. 4 million solar masses in a region smaller than the Earth-Sun distance, surrounded by a ring of plasma heated to billions of degrees. Sagittarius A is currently quiet, consuming very little material by galactic standards. But it has not always been. Enormous structures called Fermi bubbles extend above and below the galactic plane for about 25,000 light-years each. 2 lobes of hot, energetic plasma that are almost certainly the fading residue of past episodes of intense activity by Sagittarius A, when it was consuming much more material and blazing at something approaching quasar luminosities. The Milky Way's center has a dramatic past that its current quiet state does not reveal. Our Sun orbits the galactic center at about 140 miles per second, completing one full circuit in roughly 225 million to 250 million years. 1 galactic year. In the 4.5 billion years since the Sun formed, it has made perhaps 17 to 20 of these orbits. The constellations you see tonight are not the constellations that existed when the Sun was at this position in a previous galactic orbit. The stars around us are all on their own orbits, each moving at its own speed, gradually drifting relative to one another over millions of years. The night sky is not static. It is a snapshot, taken at this one moment in the Sun's long journey around the galaxy. To understand what that means, consider the galactic year. One circuit of the galactic center takes our Sun about 225 to 250 million years. The solar system formed 4.5 billion years ago. That means the Sun has completed roughly 17 to 20 laps around the galactic center since it came into existence. In the time since the last complete galactic year, here is what happened on Earth. The Cretaceous Paleogene extinction event wiped out roughly 3/4 of all species, including all non-avian dinosaurs. Continents that were once adjacent drifted to their current positions. Every mountain range on Earth either formed or was completely remade. The Himalaya did not exist as recently as 1 galactic year ago. Everything you think of as the ancient, stable geography of Earth happened entirely within the last galactic orbit. And the Sun, before that orbit? The constellations looked completely different because the nearby stars were all in different positions. The night sky, 225 million years ago, was a stranger's sky, no pattern of it matching anything we have named. The position of the Sun relative to the galactic center has changed. The arm structure of the galaxy may have shifted. The Sun has passed through different regions of the interstellar medium, some denser, some sparser, which some researchers have linked to variations in Earth's climate over geological time. Everything we think of as permanent about our galaxy, the stars we navigate by, the patterns we have named, the position we call home, is a snapshot of a system in constant motion. A slow motion measured in millions of years, but motion nonetheless. Everything about the Milky Way, its size, its structure, its star count, its dark matter halo, its central black hole, is immense, beyond any scale that human experience can easily process. And yet from here, from the surface of Earth on a clear, moonless night far from any city, the Milky Way reduces to something the human eye can actually see. A band of faint light crossing the sky. Not particularly dramatic to someone who doesn't know what it is. A slight brightening of the darkness, a suggestion of something diffuse arcing overhead. But knowing what you are looking at changes it entirely. That band is the plane of the disk, seen from inside. The stars in the direction of Sagittarius, toward the galactic center, cluster more densely, and the band brightens there, visible even from dark suburban skies as a knot of brightness in the south. Dark lanes cut through the band, where dust clouds in the disk absorb the light from stars behind them. The faint glows, the patches of slightly brighter sky within the band, are star-forming regions, regions where molecular clouds are collapsing and igniting new stars. Every feature visible in that band is something we have learned to identify and explain over the last 100 years of telescopic astronomy. Every one of them is part of the same structure we live inside. And now we need to go further. Because sitting out there in the dark, 2.5 million light-years away, is something larger. Most people, on any given clear night, never find it. You can see it without a telescope. That is the remarkable thing. It is visible to the naked human eye, but it is faint and diffuse and easy to miss if you do not know exactly where to look. Light pollution is partly responsible. For most of human history, anyone who stepped outside on a clear night would have seen the Milky Way easily, a bright band of light arcing overhead. Andromeda would have been visible to those who knew where to look, a small smudge near the familiar pattern of stars, now called the constellation Andromeda. Today, more than 80% of the global population lives under skies bright enough to prevent them from seeing the Milky Way with ease, and Andromeda, being fainter, is even harder to pick out. To see it, you need to get away from city lights. Find the great square of Pegasus in the northeastern sky on an autumn night. From the upper left star of the square, follow a chain of stars to the northeast. 2 steps, roughly, and you reach a fuzzy, elongated smudge near the star Merak. That smudge is the Andromeda Galaxy, the most distant object visible to the unaided human eye. The Persian astronomer Abd al-Rahman al-Sufi documented it in the year 964 in his Book of Fixed Stars. He described it as a little cloud. He was the first person in recorded history to leave us a description clear enough that we can be certain what he was looking at. European astronomers noted it repeatedly in the centuries that followed. In 1764, Charles Messier catalogued it as Messier 31. His catalogue was compiled to help comet hunters avoid confusing these diffuse objects with actual comets. Messier 31, obviously, was not a comet, but it was fuzzy and diffuse enough that a careless observer scanning the sky might briefly misidentify it before recognizing it was stationary. It was classified as a nebula, a word that at the time simply meant a hazy or cloudy object, without specifying its nature. And for more than a century after Messier's catalogue, its nature remained genuinely unknown. The question that consumed astronomy in the early 20th century was simple and profound. Were spiral nebulae, like Messier 31, small gas clouds within the Milky Way, or were they something else entirely? entire separate galaxies, each containing hundreds of billions of stars, at distances so vast that they appeared as faint smudges, regardless of their true size. This became the Great Debate. In April of 1920, at the Smithsonian Institution in Washington, two of the leading astronomers of the era met to formally argue their positions. Harlow Shapley had spent years mapping the distribution of globular clusters and used their positions to estimate the size of the Milky Way. His estimate was large, about 300,000 light-years across. He argued that if the Milky Way was that large, the spiral nebulae could be relatively small objects within it. Heber Curtis disagreed. He had measured the velocities of spiral nebulae and found that many were moving far faster than anything gravitationally bound to the Milky Way should be moving. He had also noted that novae, stellar explosions, were seen far more frequently in spiral nebulae than in the rest of the sky, at rates that only made sense if the nebulae were enormously distant and correspondingly large. Curtis argued they were island universes, separate systems comparable in scale to the Milky Way, just immeasurably far away. Neither man could win the debate that night. The evidence on both sides was incomplete. The tools to settle the question definitively did not yet exist. Neither Shapley nor Curtis had a way to measure distances to the spiral nebulae directly. They were both reasoning from indirect evidence, and indirect evidence admitted both interpretations. What the debate accomplished was not resolution, but clarity. It sharpened the question. If the spiral nebulae were within the Milky Way, they were unusual objects requiring explanation. If they were outside it, the universe was far larger than anyone had established, and everything astronomy thought it understood about the scale of the cosmos was, at best, the scale of a single ordinary member of a much vaster community of systems. The answer came from a mountain in California, the Mount Wilson Observatory in the hills above Los Angeles, held since 1917 the Hooker telescope, a 100-inch reflecting mirror that was, at the time, the most powerful telescope on Earth. It occupied a stone building at the peak of Mount Wilson, above much of the air that blurs starlight, fed by the clear nights of the Southern California winter. Edwin Hubble began using it to photograph Andromeda systematically. He was a methodical observer. He took plate after plate of the nebula, comparing exposures taken at different times, looking for any object that changed. Variable stars, novae. Anything that revealed itself through change was of interest. Because anything that changed had potentially measurable properties that could tell you something about distance. On October 5, 1923, examining a photographic plate, he found something. A point of light that had varied in brightness between one exposure and the next. He initially marked it as a nova, a stellar explosion. But comparing it to earlier plates, he realized it was not a nova. It was pulsating, brightening and dimming in a regular cycle. It was a Cepheid variable. Cepheid variables are stars that pulsate with a period directly linked to their true luminosity. This period luminosity relationship had been discovered a decade earlier by astronomer Henrietta Swan Leavitt. Leavitt worked at the Harvard College Observatory, where she was assigned the methodical task of cataloging and measuring stars on photographic plates. Women employed in this role were called computers. They were paid less than male observers. Their work was considered technical rather than scientific. And yet, what Leavitt found in her data was one of the most important discoveries in the history of astronomy. In this work, she noticed something extraordinary in a collection of Cepheid variables in the small Magellanic Cloud. Their pulsation periods correlated directly with their brightness. Brighter Cepheids pulsated more slowly. Dimmer ones pulsated faster. Because all the Cepheids in the small Magellanic Cloud were at roughly the same distance from Earth, the apparent brightness differences between them reflected real differences in their intrinsic luminosity. The relationship was precise enough to use as a ruler. Leavitt published her findings in 1912. If you measured a Cepheid's pulsation period, you could determine its true brightness. Compare that to how bright it appeared from Earth, and the distance followed directly from the mathematics of how light fades with distance. Hubble applied Leavitt's ruler to the Cepheid in Andromeda. He measured its period, determined its true brightness, compared that to its observed brightness, and calculated a distance. The number that came back was 900,000 light-years. His initial estimate was off, as it turned out. A systematic error in the calibration of Cepheid distances, caused by the fact that there are actually two distinct types of Cepheid variables, with different period luminosity relationships, meant the ruler was scaled incorrectly. When astronomer Walter Bade corrected this in the early 1950s, having resolved individual stars in Andromeda with unprecedented clarity after wartime blackouts, darkened the skies around Los Angeles and let him push the Hooker telescope to its limits. The distance to Andromeda jumped, more than doubled. But even Hubble's underestimate of 900,000 light-years was enough. 900,000 light-years placed Andromeda far beyond the Milky Way by any reasonable estimate of the galaxy's size. Andromeda was not a nebula within our galaxy. It was a separate galaxy. Curtis was right. The universe expanded, conceptually, in a single measurement. What Al-Sufi had called a little cloud, what Messier had catalogued to help comet hunters, was an entire separate island universe containing hundreds of billions of stars, floating in the dark at a distance that dwarfed everything previously imagined. The modern best-established distance places Andromeda at about 2,537,000 light-years. In miles, roughly 14.9 quintillion. 14.9, followed by 18 zeros. When you look at Andromeda tonight, the photons entering your eye left their source more than 2.5 million years ago. The galaxy you are seeing does not exist in its present state. You are looking at a record of what Andromeda was when early members of the genus Homo were first walking the African savanna, long before modern Homo sapiens existed. What Andromeda looks like right now, we will not know for another 2.5 million years, when the light leaving it today finally arrives. Every photograph of Andromeda ever taken is a historical document. Every observation is archaeology, conducted across 2.5 million light-years. Consider what Hubble's measurement actually meant when it was made. Before that October night, in 1923, the universe was the Milky Way. Everything that existed, every star, every cloud of gas, every object known to astronomy, was contained within a single system. The edge of the Milky Way was the edge of everything. After that measurement, the universe expanded. Not in the physical sense, though that too was about to be discovered. It expanded conceptually. The cosmos was suddenly revealed to contain other galaxies. Entire systems comparable to the Milky Way, each containing hundreds of billions of stars, scattered throughout a space so vast that even the distances between stars within a galaxy, distances requiring years of light travel, were dwarfed by the distances between the galaxies themselves. Hubble went on to discover more. By measuring galaxies beyond Andromeda and finding that almost all of them showed a redshift, that their light was stretched toward the red end of the spectrum, indicating they were receding from us, and that the more distant they were, the faster they were receding, he assembled evidence for what we now understand as the expansion of the universe itself. Space is not static. It is growing. The galaxies are not simply moving away from each other through fixed space. The space between them is stretching. Every galaxy separated from every other galaxy by enough distance is being carried further away, not by its own velocity, but by the expansion of the medium it occupies. All of this came from the same chain of observation. Al-Sufi saw a little cloud. Messier catalogued a diffuse object. Leavitt found the ruler in the period-luminosity relationship. Hubble applied it. And the universe turned out to be incomprehensibly larger than anyone had suspected, filled with island universes, each containing hundreds of billions of stars, separated from each other by voids so vast that the void between us and Andromeda, which we have been exploring tonight, is merely a local gap between two nearby neighbors. Now, look at Andromeda as a structure, not a smudge. It is a spiral galaxy, like the Milky Way. It has a disk of stars, gas, and dust organized in spiral arms around a central bulge. It has its own central bar of stars. It has a stellar halo. It has satellite galaxies orbiting it. It has its own central supermassive black hole. But in almost every dimensional comparison with the Milky Way, Andromeda is larger. The disk of Andromeda spans somewhere between 220,000 and 260,000 light-years across. Compare that to the Milky Way's roughly 100,000 to 120,000 light-years. Andromeda's disk is more than twice the diameter of our own galaxy. Where we have a thin disk, roughly 1 to 2,000 light-years thick, at its densest, Andromeda's disk is also thin in proportion, but scaled to its much larger diameter. The spiral structure of Andromeda differs from ours in ways that reflect its history. Andromeda shows evidence of past gravitational disruptions, probably from interactions with its satellite galaxies. Its spiral arms are not perfectly symmetric. One of its closest companion galaxies, M32, may have punched through Andromeda's disk in the relatively recent past, on a timescale of hundreds of millions of years, disturbing the outer disk and triggering star formation in rings visible in infrared observations. The central bulge of Andromeda is large and prominent. It is dominated by old, reddish stars that formed early in the galaxy's history, and it is considerably more massive and prominent than the smaller bulge of the Milky Way. Both galaxies have been building up over billions of years by absorbing smaller systems, and both bear the traces of those absorptions in their halos and stellar streams. Its stellar halo extends even further. Observations using wide-field surveys have traced stars associated with Andromeda's halo to distances of more than 1,300,000 light-years from its center. Consider what this means spatially. Andromeda's center is 2,537,000 light-years from Earth. Its halo extends 1,300,000 light-years from that center. On the side of Andromeda facing us, its outermost halo material is roughly 1,237,000 light-years away. The outermost fringes of Andromeda's halo and the outermost fringes of the Milky Way's halo may already be in contact. In a very real sense, the two galaxies are already touching. even though their bright disks are still separated by more than 2 million light-years. This halo contact is not dramatic. There are no explosions, no visible disturbances at the centers of either galaxy. The halo stars of each system are so sparse, so widely separated, that the interpenetration of the two halos produces nothing that could be seen. A few stars from Andromeda's outermost halo may be drifting through regions that would be considered technically within the Milky Way's outer halo, and vice versa. But this contact is a gravitational reality, even if it is observationally invisible. The halos are interacting. The gravity of each galaxy is shaping the distribution of the outermost stars and dark matter in the other. When astronomers model the merger that is coming, they start not with the disks colliding, but with the halos that are already overlapping, already influencing each other, already slowly distorting the trajectories of the most distant stars in both systems. In a sense, the merger has already begun. We just live on timescales that cannot perceive it. Andromeda has satellite galaxies of its own. The most prominent are M32 and M110, both small elliptical companions visible near Andromeda in even a modest telescope. Andromeda has at least 14 known satellite galaxies orbiting it, analogous to the Magellanic Clouds and other dwarf companions of the Milky Way. When the Milky Way and Andromeda merge, all of these satellite systems will be swept into the combined gravitational field of the merged galaxy, their orbits disrupted, some of them eventually absorbed into the halo of Andromeda, contributing yet another layer to the already complex stellar archaeology of what will become one enormous elliptical remnant. And Andromeda has a feature that has no obvious equivalent in the Milky Way. A vast tidal stream, sometimes called the Andromeda Stream or the Great Southern Stream, arcing across the southern halo of the galaxy. This stream is thought to be the remains of a small galaxy that Andromeda absorbed perhaps 1 to 2 billion years ago. Tidal forces from Andromeda stretched the infalling galaxy into a long ribbon of stars that was then scattered through the halo as debris. The stream is still visible. It is one of the most prominent tidal features around any nearby galaxy, a written record in starlight of a consumption that happened in the deep past. The Milky Way has done the same thing. The Sagittarius Stream, the debris trail from the Sagittarius dwarf spheroidal galaxy, arcs around our own galaxy in a similar pattern. Both great spirals are ancient consumers, incorporating smaller systems into themselves over billions of years. Andromeda's star count is estimated at around 1 trillion stars. That is roughly 2 to 5 times the number of stars in the Milky Way, depending on which estimates you use. 1 trillion stars. If you wanted to count them one per second, starting now, you would finish in roughly 32,000 years. That is not a particularly illuminating comparison, but it gives you a sense of the number. And it is worth being clear about what a star is. Each one is a nuclear furnace, converting hydrogen into helium through the same process that powers our sun, radiating energy at rates ranging from fractions of our sun's output to tens of thousands of times its luminosity. Each one is, in principle, a potential gravitational anchor for a planetary system. Many of them have planets. Billions of those stars, in Andromeda alone, may have planets orbiting in zones where liquid water is stable. Whether any of them host life, whether any of those planets have evolved anything that can look back in our direction and wonder about this smudge in their own sky, we have no way to know. But star count is not the same as total mass. When you include the dark matter halos surrounding both systems, the mass comparison shifts. current estimates of the Milky Way's total mass, including its dark matter halo, fall in the range of roughly 800 billion to 1 trillion solar masses. Andromeda's total mass appears to fall in a similar range, or perhaps somewhat lower. Some analyses suggest the Milky Way may actually be the more massive of the two systems, despite having fewer stars. The dark matter halos dominate the mass budgets of both galaxies, and they are notoriously difficult to measure, precisely because dark matter does not emit light, and its distribution must be inferred from gravitational effects. Both galaxies, when you include their dark matter halos, contain roughly similar amounts of material. Two comparable islands of stars and dark matter, separated by 2.5 million light-years, gradually approaching each other through a void so empty it barely qualifies as a medium. What is not in doubt is Andromeda's central black hole. Formerly designated M31 star, Andromeda's central supermassive black hole has a mass of approximately 140 million solar masses. Sagittarius A, at the center of the Milky Way, has a mass of about 4 million solar masses. Andromeda's black hole is roughly 35 times more massive, 140 million solar masses. When this black hole was actively feeding in Andromeda's earlier history, it would have blazed as a luminous quasar, outshining the entire surrounding galaxy and visible across enormous distances. The Hubble Space Telescope revealed something unexpected about Andromeda's nucleus when it imaged the core in detail. The nucleus appeared double, two distinct brightness peaks, extremely close together, where a single central concentration was expected. The explanation that emerged from detailed modeling involves an eccentric disk of old red stars orbiting the central black hole. Stars on elliptical orbits spend more time near the far end of the orbit, where they move slowly, than near the close end, where they move fast. This creates an asymmetric distribution of stellar density around the black hole. When viewed from our angle, this asymmetry creates the illusion of two separate brightness concentrations. The black hole is single. The nucleus is single. The appearance of two centers is an artifact of orbital mechanics, not evidence of two objects. It is one of the more elegant examples of how the mathematics of orbits can produce a surprising appearance from a relatively simple physical situation. And all of this, the disk, the halo, the satellite galaxies, the tidal streams, the peculiar double nucleus, the 140 million solar mass black hole at the center, all of it is headed toward us. Between the Milky Way and Andromeda lies a gap. Not a gap in the way that word usually implies, something bridgeable, something that shrinks when you move toward it. This gap is of a different order. 2.5 million light-years of intergalactic space. Within our own galaxy, the space between stars is already extraordinarily empty by any measure we can apply. The interstellar medium, the thin mix of gas and dust filling the galaxy between star systems, averages roughly 1 atom per cubic centimeter. The best vacuum ever created in a laboratory on Earth still contains billions of molecules per cubic centimeter. The space between stars is already far more empty than anything we can manufacture. But the space between galaxies is different again. The intergalactic medium in the region between the Milky Way and Andromeda has a density of roughly 1 hydrogen atom per cubic meter. 1 cubic meter is the volume of a washing machine. 1 atom per washing machine. In some regions, even that estimate is generous. This is as close to true emptiness as the universe appears to allow. And yet, this space is not featureless. It contains structure, invisible but real. Dark matter filaments, the scaffolding of the cosmic web, thread through intergalactic space. On the very largest scales, matter in the universe is not distributed uniformly. It is organized along vast sheets, walls, and filaments separated by enormous empty voids. This structure, the cosmic web, reflects the initial tiny fluctuations in density from the earliest moments of the universe, amplified over billions of years by gravity into the enormous structures we see today. The Milky Way and Andromeda sit embedded in one small region of this web, part of what astronomers call the local group, a gravitationally bound collection of more than 50 galaxies dominated by the two large spirals. Between those two spirals, threading through the intergalactic medium, there are faint dark matter filaments connecting the two systems. These are not visible. They will not be detected directly by any instrument we currently have. But they are there, providing the gravitational framework that has kept the Milky Way and Andromeda bound to each other across billions of years of cosmic expansion. In the visible domain, scattered through the intergalactic dark, there are rogue stars. Individual stars not belonging to any galaxy, drifting alone through the space between galaxies. They got there through gravitational interactions. When two galaxies pass near each other, or when a star is ejected from its host galaxy by interaction with a massive black hole, or by the orbital chaos of a star cluster, it can receive a kick large enough to escape the galaxy entirely. That star then continues on its trajectory, indefinitely, through intergalactic space. It burns. It still emits light. But there are no planets around it to receive that light. There is no nearby gas to illuminate. It is alone, in a dark so complete that no words available to us adequately describe it. Some estimates suggest intergalactic stars may account for a meaningful fraction of all the stars in the universe, solitary wanderers floating in the voids between galaxies, visible to no one. What does that actually mean? A star, like our sun, produces light. It radiates energy continuously, enormous amounts by any human standard, in all directions. In the intergalactic void, that light goes nowhere. It does not illuminate a planetary system. It does not warm a surface where chemistry could happen. It travels outward at 186,000 miles per second and simply keeps going, spreading out, fading, eventually diluting to nothing against the background of the universe. The light from a rogue star is light that serves no purpose in any biological sense. It is evidence that the universe is indifferent to the question of whether its processes produce anything that can witness them. The local group also contains smaller galaxies between the two dominant systems. The Triangulum galaxy, M33, is the third largest member of the local group, a smaller spiral roughly 2,700,000 light-years away. Dozens of dwarf galaxies orbit one or the other of the two main systems, or drift on their own trajectories within the local group. Some of these dwarf galaxies are ancient, their star formation exhausted billions of years ago. Others are still forming stars in slow, dim bursts. They are scattered throughout the local group at various distances, distributed across a region perhaps 10 million light-years in diameter. But none of these intermediate systems are large enough or positioned in a way that would serve as any kind of waypoint between the Milky Way and Andromeda. The 2.5 million light-years between the bright disks of the two galaxies is, for all practical purposes, a void. 1 atom per cubic meter. Faint, dark matter filaments. The occasional solitary star, burning alone. Nothing that helps you across. Now here is what makes all of this specific to this moment in history. Andromeda is not simply out there. It is approaching. When astronomers measure the spectra of most distant galaxies, what they find is a redshift. Light from receding objects is stretched toward longer, redder wavelengths. The universe is expanding. Space itself is stretching, and as it stretches, it carries galaxies apart. The farther away a galaxy is, the faster it appears to be receding, because more space is expanding between us and it. Almost every galaxy we have observed shows this redshift. Andromeda does not. Andromeda's light is blue-shifted. Its light waves arrive compressed toward shorter, bluer wavelengths. The only explanation for blue shift is that the source is moving toward the observer. Andromeda is not receding. It is approaching. The first person to measure this systematically was Vesto Melvin Slipher. Working at the Lowell Observatory in Flagstaff, Arizona, in 1912, he was conducting a program of measuring the spectra of spiral nebulae. This was careful, methodical work. Each observation required hours of exposure time on photographic plates, capturing enough light from these faint diffuse objects to detect the subtle shifts in spectral lines that would reveal their velocities. Slipher was working at the limits of what was technically possible, and he knew it. When he analyzed the spectrum of Andromeda, the blue shift was unmistakable. He calculated an approach velocity of roughly 186 miles per second. At the time, Slipher did not know what these objects were. He was measuring the velocities of things whose nature was still unknown, things that would not be confirmed as separate galaxies until Hubble's work a decade later. But the measurement itself was solid. Here was something, whatever it was, moving toward us at roughly 186 miles per second. Slipher went on to measure the spectra of other spiral nebulae and found something equally striking. Most of them were moving away, not toward us, away, and moving away at speeds far higher than anything in our galaxy. Slipher's velocity measurements of dozens of spiral nebulae would eventually contribute to the discovery of the expansion of the universe, though Slipher himself did not draw that conclusion. That step came later, from Hubble, but Andromeda stood apart from the rest. In a universe where, as subsequent observations would show, almost everything is moving away, here was a galaxy coming toward us. Modern measurements, far more precise than Slipher's, give an approach velocity of approximately 68 miles per second. That is about 245,000 miles per hour. Fast enough to circle the Earth roughly 10 times in a single hour. And yet the distance is so immense that even at this speed, meaningful progress takes geological timescales. Over the entire span of human civilization, roughly 12,000 years, Andromeda has closed the gap by about 26 trillion miles. 26 trillion miles sounds large. It is approximately 4 light-years out of 2.5 million, a fraction of a percent of the total distance. The approach is real. The speed is real. But the gap is of an entirely different order of magnitude. For a long time, astronomers were genuinely uncertain whether the two galaxies were actually on a collision course. Measuring the component of Andromeda's velocity directly toward or away from us, its radial velocity, is what gives us the blue shift measurement. That part is clear. But Andromeda could also be moving sideways across the sky, and if that sideways motion were large enough, the two galaxies might pass near each other without a direct collision. Measuring that sideways velocity, the transverse velocity, is extremely difficult. The motion is so small, projected against a distance of 2.5 million light-years, that it requires extraordinary precision to detect. A team led by astronomer Roland van der Merel used the Hubble Space Telescope to make that measurement. They tracked the precise positions of individual stars in Andromeda over a baseline of several years, looking for the tiny but detectable shift in position that would reveal how Andromeda was drifting across the sky. The results, published in 2012, showed that Andromeda's transverse velocity was small. It was not moving significantly sideways relative to our line of sight. It was moving almost directly toward us. When this measurement was incorporated into gravitational simulations, the results were consistent and clear. The Milky Way and Andromeda are on a near head-on collision course, not a near miss. A merger. The current best estimate for the timing of the first close approach is roughly 4 billion to 4.5 billion years from now. The uncertainty reflects the remaining uncertainty in the total masses of both galaxies, particularly their dark matter halos, and the small residual uncertainty in the transverse velocity. But across all plausible values of those uncertainties, the collision appears essentially inevitable. And it will not begin with the disks meeting. The dark matter halos of both galaxies, which extend far beyond the visible disks, already overlap. The dark matter halo of the Milky Way extends to perhaps 300 to 500,000 light-years from our galactic center. Andromeda's halo extends at least as far, possibly to 1,300,000 light-years or more. With the two galaxy centers separated by roughly 2,537,000 light-years, the outermost edges of both halos have been interpenetrating for billions of years. Gravity is already connecting the two systems across the void. The tidal forces each galaxy exerts on the other are already subtly distorting the distribution of matter at the outermost edges of both systems. Though these effects are too small to be easily distinguished from the background noise of other gravitational influences. Over the next billion years, those tidal effects will grow stronger. Over 2 billion years, they will become measurable in the positions and velocities of the outermost halo stars. 3 billion years from now, the outer disk of both galaxies will begin to feel the pull. 4 billion years from now, the visible disks of both galaxies will be drawing unmistakably toward each other, the sky above Earth, or whatever exists here beginning its transformation. As the approach continues, over billions of years, that gravitational pull will intensify, distorting the outer structures of both galaxies, pulling material outward in tidal streamers, and eventually drawing the bright disks of both systems into the same region of space for the first time. What actually happens when two galaxies merge? The answer is counterintuitive, and it is important to get this right before the imagination fills in the wrong picture. Two galaxies colliding does not look like two solid objects colliding. Galaxies are not solid. They are not even dense in any meaningful sense. A galaxy is almost entirely empty space, organized by gravity. The stars within a galaxy are separated by distances measured in light-years. In our region of the Milky Way, the nearest star to our Sun is 4.24 light-years away. Scale everything down so that the Sun is the size of a period at the end of a sentence. At that scale, Proxima Centauri would be another period roughly 2 miles away. 2 miles of nothing between two punctuation marks. That is how sparse a galaxy actually is. When two galaxies interpenetrate, the stars almost never encounter each other directly. The probability of any individual star colliding with another star during a galaxy merger is extremely small. Our Sun and the Earth will almost certainly never come close to another star throughout the entire process of the Milky Way and Andromeda merging. What does happen is gravitational. And at the scale of two entire galaxies, the gravitational effects are profound, even if they unfold slowly by any human measure of time. As the Milky Way and Andromeda draw together, the gravitational field of each begins to distort the structure of the other. Stars on the outskirts of both galaxies feel the pull of the approaching system and begin to deviate from their normal orbits. The disk structures warp. Long tidal tails of stars get drawn out of each system. Streams of stellar material, pulled by the tidal forces of the approaching galaxy, and then trailing behind as the systems continue their approach. Tidal tails can extend for hundreds of thousands of light years. They are one of the most visually distinctive signatures of interacting galaxies, and we can see them right now in other merging pairs throughout the universe. The antennae galaxies, two spirals currently merging about 45 million light-years from Earth in the constellation Corvus, show exactly this structure. Two bright galactic cores, surrounded by a chaotic tangle of tidal streams and bridges of stellar material, with two long antenna-like tails extending outward from the main bodies. This is what the Milky Way and Andromeda will look like from outside during their own merger, if there was something far enough away to observe it. While the stars are being gravitationally reorganized, the gas in both galaxies is doing something different. Stars pass through other stars' positions without interacting. Gas does not do this. When gas clouds encounter other gas clouds, they collide and compress. The shock of this collision triggers cooling, which triggers the collapse of dense clumps, which triggers the formation of new stars. The gas collisions between the Milky Way and Andromeda will ignite an enormous burst of new star formation, far more intense than either galaxy currently produces individually. New stars will form at elevated rates in the compressed gas regions, concentrated where the gas density and collision velocity produce the greatest compression. The new stars born in these bursts are often massive and luminous. They burn brilliantly for only a few million years before exhausting their fuel. As they go, many of the most massive will collapse and produce supernovae, seeding the surrounding gas with heavy elements forged in their cores. A galaxy in the starburst phase of a major merger is one of the brightest kinds of objects in the local universe. The most extreme examples we observe in the nearby universe shine in infrared light, with luminosities exceeding those of entire undisturbed galaxies by a factor of 10 or 100. This is what happens when you force the compressed gas of two galaxies through each other. Every element heavier than hydrogen and helium that exists on Earth, every atom of carbon, oxygen, nitrogen, iron, calcium, silicon, all of it was forged inside a star and scattered by a supernova or a stellar wind. The starburst, triggered by the Milky Way and Andromeda merger, will produce vast quantities of these heavy elements, seeding the merged galaxy's gas for billions of years of future star formation. The stars that form in the merger starburst will not be our Sun's modest cousins. Many will be massive, hot, short-lived, and brilliant. And when the most massive of them end, they will enrich the surrounding gas with the elements their interiors synthesized. In this sense, a galaxy merger is not just destructive, it is generative. It shuffles the cards and deals a new hand. The central black holes of both galaxies will not be passive during this process. As the gravitational disruption drives gas inward toward the centers of both galaxies, Sagittarius A and M, 31 star, may both enter periods of elevated activity. Gas and stellar debris falling onto a supermassive black hole releases enormous amounts of energy as radiation. The efficiency of this process is remarkable. When matter falls into a supermassive black hole, the conversion of mass to energy through radiation is far more efficient than any other process in nature, including nuclear fusion. A few percent of the infalling mass is converted directly to radiated energy. When this process is intense enough, the result is an active galactic nucleus, a blindingly luminous core that can outshine the entire surrounding galaxy. At its most extreme, this is a quasar. Whether either black hole will reach quasar luminosities during the merger depends on how much gas actually reaches the central regions, which the simulations cannot precisely predict. But periods of significantly elevated activity are plausible for both. After multiple gravitational passes, over hundreds of millions of years, as the two systems gradually lose energy to dynamical friction and begin their final convergence, the two central black holes will find themselves in the nucleus of the merged system. They will not immediately merge with each other. They will form a binary, two supermassive black holes orbiting each other in the dense central region of the combined galaxy. The orbital period of this binary could be anywhere from a few years to a few thousand years, depending on how close together they end up after the dynamical friction process. Two supermassive black holes, each surrounded by stars and gas, slowly spiraling toward each other in the center of a newly formed elliptical galaxy. The binary will lose energy over time through a process called dynamical friction as the two black holes interact with the surrounding stars. Stars that pass near the binary can receive a gravitational kick and be ejected from the central region at high velocity. Each ejected star carries away a small amount of orbital energy from the binary, tightening its orbit incrementally. This process continues until the binary has ejected enough stars that there are few left to interact with, which can create what astronomers call the final parsec problem, whether stars, gas inflow, or other effects ultimately drive the binary to separation. Small enough for gravitational wave in spiral to take over is an open question in theoretical astrophysics. But the outcome is not in doubt. It will also lose energy through the emission of gravitational waves, the ripples in spacetime predicted by Einstein's general theory of relativity. When the two black holes are separated by roughly a few hundredths of a light year, gravitational wave emission begins to dominate all other energy loss mechanisms. At that point, the inspiral accelerates. The orbit shrinks. The gravitational wave frequency increases. The amplitude increases. And then, after a process that may take hundreds of millions of years, the two black holes will come close enough for gravitational wave emission to rapidly drain the remaining orbital energy. They will merge. In a fraction of a second, two objects that each took billions of years to build will combine into one. A pulse of gravitational waves, enormously energetic, will radiate outward from the merged center. The signal will be far stronger than anything the LIGO and Virgo detectors have recorded from the much smaller black hole mergers they have detected in recent years. Strong enough, potentially, to be detected by a civilization that would not exist for billions of years yet. The final object will be a single supermassive black hole with the combined mass of both Sagittarius A and M, 31 star, roughly 144 million solar masses in a single point, and the galaxy surrounding it, which astronomers have nicknamed Milkomeda, will no longer look like either of its parents. The spiral arms that make both the Milky Way and Andromeda so visually distinctive will be gone, disrupted and scattered by the multiple gravitational passes. Stars that had orbited their respective galactic centers on orderly, nearly circular paths for billions of years will have been redirected onto chaotic, elongated trajectories. The orderly disk structure will have been destroyed. The result will be an elliptical galaxy, a smooth, roughly egg-shaped cloud of stars slowly settling into a new equilibrium. Elliptical galaxies are dominated by old, reddish stars. Most of the gas available for new star formation will have been consumed in the starburst phases of the merger. The remaining population will be aging stars, growing cooler and redder over billions more years. Milky will be a very different kind of structure from either of its parents. Ancient in appearance, settled, enormous. The entire process, from the first close passage, roughly 4 to 4.5 billion years from now, to the final settling of the merged system, will span roughly 2 billion years. Think about what that means in context. The Sun formed 4.5 billion years ago. In the time it took the Sun to form and run for 4.5 billion years, the merger process will unfold and complete. When it is over, the Sun will still be burning. It is a middle-aged star, with roughly another 5 billion years of fuel remaining. It will outlive the merger. It will continue to shine in whatever portion of the merged galaxy the gravitational disruption assigns it to. And Earth will orbit it throughout. The gravitational forces acting during the merger are real and large, but they act on the scale of galaxies. They pull stars to new orbits. They warp disk structures. They draw tidal tails of stars, hundreds of thousands of light-years long. And when the Sun's orbit is disrupted, when the ordered, nearly circular path it currently follows is replaced by something more erratic and elongated, the solar system moves with it as a unit. There is no mechanism in the merger that selectively disrupts the relationship between the Sun and its planets without disrupting the whole. The solar system is bound together by gravity, far stronger than anything the galactic tidal forces can impose. The orbits of the planets around the Sun require an encounter with another star passing at close range to be significantly disturbed, and as we established, the probability of that happening during the merger is extremely small. These forces are vast enough to reorganize entire galaxies, but they operate so smoothly and uniformly across the tiny volume of a single solar system that the 8 planets in their orbits will not feel them in any meaningful way. The solar system will remain intact. The sky above it will not be recognizable. Long before the first close passage of the galactic disks, as Andromeda draws close enough for its disk to become visible to the naked eye, the night sky will begin to change. The process is gradual enough that no individual lifespan would perceive it. But on timescales of hundreds of millions of years, the transformation will be profound. About 1 billion years from now, Andromeda will have grown bright enough that its disk spans a wider arc in the sky than the Milky Way's central band does today. A growing band of light. An external galaxy's disk, visible above the horizon. Something humans have never seen. Something no biology on this planet has ever evolved to process. 2 galactic disks visible simultaneously. And then, over the billions of years of the merger proper, the sky will transform entirely. 2 galactic cores visible simultaneously. Tidal tails arcing overhead. New star-forming regions blazing with hot young stars. The ancient patterns of tonight's sky, the constellations that human beings have named and navigated by for tens of thousands of years, will be gone. Not erased, suddenly. Erased over spans so long that each generation, if there were generations left to notice, would see a sky virtually identical to the one their grandparents saw. But averaged over millions of years, the drift would be undeniable. The stars that make up Orion, Cassiopeia, the Big Dipper. All of them will have scattered to new orbits over the billions of years involved. New patterns will exist, formed by stars that have not yet been born. The sky of the merger era will be a stranger's sky. But whatever is alive to look at it will be looking at something extraordinary. Two ancient spiral galaxies, two island universes that spent billions of years apart, finally becoming one. And now we arrive at the question that everything about Andromeda eventually leads to. Can we ever go there? Not watch the merger happen billions of years from now. Not observe Andromeda from here. Not send a signal that might, given enough time, reach it. Actually travel to it. Actually cross the 2.5 million light-years of intergalactic void between our galaxy and Andromeda's disk and arrive. Stand on a planet in Andromeda's disk, or orbit through its halo, or approach its spiral arms from outside, the way we see them in photographs. The honest answer, once you follow the physics all the way through, is effectively no. Not no, pending better technology. Not no without a sufficiently long timeline. No, in a way that becomes more absolute the more carefully you examine it. And the reason is not one single obstacle. It is a cascade of obstacles, each one independently insurmountable, stacked on top of each other, so that resolving any one of them still leaves all the others intact. Start with the spacecraft we have. Voyager 1 is currently the most distant human-made object in existence. Launched September 5th, 1977. It has been in continuous travel for nearly 50 years. In 2012, it crossed into interstellar space beyond the heliopause, becoming the first human artifact to enter the medium between stars. It is currently moving at approximately 38,000 miles per hour relative to the Sun, about 10.6 miles per second. That is the sustained speed of our fastest long-duration spacecraft. It is genuinely fast by any comparison available to human experience. If you could drive a car at 38,000 miles per hour, you would circle the Earth in about 40 minutes. You would cross the entire United States in about 6 minutes. You would travel from here to the Moon in about 6 hours. And yet, Voyager 1 has been traveling at this speed for nearly 50 years. It has covered roughly 15 billion miles. It is just now, after half a century of uninterrupted flight, leaving the edges of our own solar system. It has not yet reached the Oort cloud. The Oort cloud's outer edge is 9 trillion miles away. Voyager 1, after 50 years, has covered only a small fraction of 1% of the distance to the outer boundary of our own solar system. Now apply that velocity to the distance to Andromeda. Andromeda is approximately 14.9 quintillion miles away. At 38,000 miles per hour, the transit time works out to approximately 44 billion years. The current age of the universe is about 13.8 billion years. A Voyager-class spacecraft heading toward Andromeda would need to travel for more than 3 times the current age of the universe to arrive. By the time it got there, assuming the craft could somehow survive that long, the universe itself would be unrecognizable. Stars would have burned out and gone cold. The merger of the Milky Way and Andromeda would have long since completed. The merged galaxy Milky would have aged into something different from what it was when the spacecraft left. Andromeda, as a distinct object, would not exist anymore. This is not a gap that better engineering bridges. It is a statement about what the phrase 2.5 million light-years actually means in terms of time and velocity. Could we build something faster? In principle, yes. Nuclear pulse propulsion. The concept of detonating nuclear devices behind a spacecraft and absorbing the shockwave to generate thrust was studied seriously in the United States under Project Orion, beginning in the late 1950s. The physics are sound. Computer models suggested a system like this could accelerate a very large spacecraft to several percent of the speed of light. At 3% of the speed of light, a journey to Andromeda takes approximately 83 million years. 83 million years. The non-avian dinosaurs went extinct about 66 million years ago. At 3% of light speed, the journey to Andromeda takes longer than the entire span since that extinction, with time left over. Fusion drives could theoretically do better. Fusion is the process that powers stars, and it is far more energetically efficient than fission or chemical reactions. The British Interplanetary Society's project, Daedalus, studied in the 1970s, proposed a fusion-driven probe that could reach roughly 12% of the speed of light. At 12% of light speed, the transit time to Andromeda is about 21 million years. That is roughly 3 times longer than the entire span since the earliest human ancestors diverged from other apes. Antimatter engines represent the most energetically efficient propulsion concept known to physics. When matter and antimatter meet, they annihilate completely, converting 100% of both their masses into energy. No other reaction comes close to this energy density. A sufficiently powerful antimatter engine could, in principle, push a spacecraft to a very high fraction of light speed. The problem is production. Every particle accelerator on Earth combined has produced, across the entire history of particle physics, a total amount of antimatter with the energy equivalent of a few hundred joules, enough to briefly light a single light bulb. Scaling this to the tons of antimatter a spacecraft would need is not a matter of building bigger accelerators. It would require energy sources and production methods that do not exist and have no clear path to existing. There have also been proposals for laser-pushed light sails. The Breakthrough Starshot initiative, announced in 2016, proposed using an array of powerful ground-based lasers to push a tiny, ultra-thin sail to roughly 20% of the speed of light. This is one of the most technically credible proposals for achieving very high velocities, at least for tiny payloads. 20% of light speed is extraordinary by any measure. At 20% of light speed, the transit time to Andromeda is about 12.5 million years. 12.5 million years of continuous, uninterrupted travel for a sail the size of a postage stamp, carrying no significant payload. A generation ship, in the conventional meaning, houses a self-sustaining human population over multiple generations. The concept has been seriously studied for journeys of a few hundred years, maybe a few thousand. The biological, social, and psychological challenges, even at those timescales, are formidable. At 12 million years, the word generation ship stops meaning anything coherent. In 12 million years, the passengers would have gone extinct or transformed into something unrecognizable, or diverged into separate species under the pressures of whatever selective forces operate in a closed population aboard a spacecraft for millions of years. No mission launched with a destination in mind, 12 million years later, can be described as a mission in any meaningful sense. To put this in the starkest terms, the span from the earliest recognizable ancestors of humans to modern Homo sapiens is roughly 4 to 6 million years. In 12 million years, whatever lived long enough to arrive at Andromeda would bear no more relationship to us than we bear to something that existed before our genus had formed. They would not remember what Earth was. They would not have any cultural continuity with the civilization that launched them. They would be a different kind of life, shaped by 12 million years of selection inside a spacecraft, with a biology and a psychology designed by conditions we cannot predict. This is not a generation ship problem. This is something there is no word for, because nothing in the history of biological life on Earth offers a precedent for it. The bacteria that colonized the first land surfaces did not have intentions. Evolution does not remember destinations. A voyage of 12 million years is not an extended human mission. It is a geological era, during which whatever living thing is aboard will become something else entirely, without any guarantee that what it becomes will still care about Andromeda. And even if you remove the biological constraints entirely and sent a machine, the problems do not disappear. Cosmic radiation and the interstellar and intergalactic medium degrade materials over millions of years. Any known material eventually fails under prolonged exposure to the high-energy particles permeating interstellar and intergalactic space. Semiconductor-based computing systems are especially vulnerable. No known architecture for electronic components remains functional across spans of millions of years under radiation exposure. And even a probe that somehow arrived intact after 12 million years would need to send a signal back. That signal, traveling at the speed of light, would take another 2.5 million years to reach Earth. By the time any return signal arrived, over 14 million years would have passed since launch. No civilization has existed for 14 million years. Complex animal life on Earth has only been around for about 540 million years, and the vast majority of that time involved animals that bore no resemblance to anything that would launch a spacecraft. Then there is relativity. Einstein's special theory of relativity contains a phenomenon called time dilation. When an object moves at a significant fraction of the speed of light, time passes more slowly for that object than for a stationary observer. The faster the object moves, the more pronounced the effect. At 90% of light speed, a traveler's clock runs at roughly 43% the rate of a stationary clock. At 99%, about 14%. At 99.9%, about 4.5%. Pushed to 99.9999% of light speed, and the traveler ages less than 1 year for every 700 years that pass outside. This means that in principle, a traveler moving fast enough could experience the crossing to Andromeda as taking only tens of thousands of years rather than millions. At 99.999% of light speed, the traveler might experience only a few hundred years of shipboard time. But back at Earth, over 2.5 million years would still pass. Whatever sent them is long gone by the time they arrive. The civilization that built the spacecraft. The language in which the mission was conceived. The planetary arrangements of the solar system. All gone. Whatever biology might once have lived on Earth will have changed beyond recognition. The Sun, by that point, will have aged 2.5 million years closer to its eventual end. Arriving at Andromeda is arriving in a future that bears no relation to the present. And the practical barriers to reaching those speeds are not surmountable with any technology we can envision. To accelerate 1 kilogram of mass to 99% of the speed of light requires roughly the energy equivalent of thousands of nuclear bombs of Hiroshima scale. A crewed spacecraft is not 1 kilogram. It is millions of kilograms. The fuel itself must be accelerated alongside the payload, which means you need more fuel to push the fuel, in a cascade that turns the energy requirements astronomical. This cascade gets worse as you push toward higher velocities. At 99% of light speed, the relativistic mass increase makes further acceleration increasingly expensive. At 99.9%, the energy requirement is roughly 3 times higher than at 99%. At 99.99%, more than 10 times higher than at 99%. The equations do not simply scale up, they get steeper. And the higher the final velocity, the more extreme this cascade becomes. There is no plausible energy source for achieving near-light velocities for any macroscopic object. Not nuclear fission, not fusion, not antimatter, not any theoretical energy source we have even the sketch of an idea for. The total energy output of the Sun over its entire 10 billion year lifetime would not be sufficient to accelerate a large crewed spacecraft to a significant fraction of light speed. There is also the problem of what you travel through. At 99% of light speed, the sparse hydrogen atoms floating in the intergalactic medium are not gentle obstacles. They strike with the energy of high-energy cosmic rays. Each hydrogen atom, at that relative velocity, delivers a punch to the front of the spacecraft equivalent to a particle from a high-energy accelerator. Over the course of a multi-million-year voyage, the cumulative bombardment is extraordinary. The cumulative radiation dose over a voyage of millions of years would destroy any material and any crew long before arrival. Shielding helps, in principle, but shielding adds mass. More mass requires more energy to accelerate. More fuel requires more shielding for the fuel. The cascades compound rapidly into physical impossibility. And, finally, the universe itself is not a fixed backdrop. Space is expanding. Dark energy is driving galaxies apart at rates proportional to their distance. The universe has a built-in expansion, measured by the Hubble constant, which describes how fast space is stretching per unit distance. Beyond a certain distance, the expansion of space between us and a distant object exceeds the speed of light. This does not violate relativity because it is not objects moving through space. It is space itself expanding. There is a boundary, called the cosmological event horizon, beyond which we can never send a signal or reach any object. Because the space between us and everything beyond that horizon is expanding faster than light can travel. Andromeda is well within our event horizon. We can see it. We can potentially, in principle, send a signal that would arrive before the horizon swallows it. But for any spacecraft moving slowly enough, and slowly here means anything we could realistically build, the expansion of space adds to the effective distance over the course of a very long voyage. A spacecraft traveling at 100 miles per second would need to cover a total distance that keeps growing as it travels, because space is expanding behind and around it. There is a minimum velocity threshold below which a spacecraft heading from the Milky Way toward Andromeda would never actually arrive, because the expansion of space would carry the destination away faster than the spacecraft could approach it. Current estimates put this threshold at a few hundred miles per second. Voyager 1, our fastest sustained spacecraft, moves at about 10.6 miles per second. Andromeda, from Voyager's perspective, is not getting closer. The universe is expanding fast enough that the net distance between Voyager and Andromeda is actually increasing. This is not a problem Voyager could solve by pointing itself in Andromeda's direction. Voyager will never reach Andromeda. Not in any time frame. Not in any version of the future that the laws of physics, as we understand them, permit. This is not Voyager's fault. It is the physics of the universe expressing itself honestly. Physics is consistent about all of this. Not selective. Not arbitrary. The same equations that let us calculate Andromeda's distance, structure, velocity, and future path also describe, with the same precision, why reaching it is not possible within any framework our civilization can conceive. The distance to Andromeda is not a technological barrier waiting for a better rocket. It is a statement about the structure of the universe we inhabit. And yet, the light comes to you. Every night that the sky is clear and the moon does not wash it out, photons from Andromeda arrive at Earth. They travel 2.5 million light-years, cross the intergalactic void at 186,000 miles per second, pass through our galaxy, pass through our solar system, and enter the eyes of anyone looking in the right direction. That crossing, which no spacecraft could complete in less than tens of millions of years, photons accomplish continuously, every night, for free. And they carry real information, not just brightness, not just direction. The spectrum of Andromeda's light tells us the chemical composition of its stars. Different elements absorb and emit light at specific wavelengths, and those wavelengths are encoded in the light that crosses 2.5 million light-years to reach us. From that spectrum, we can determine that Andromeda contains stars like our Sun, red giant stars, blue supergiant stars, and stellar populations that formed at different epochs in the galaxy's history. We can measure the velocity of different parts of the galaxy by noting the Doppler shift of specific spectral lines. The parts of Andromeda rotating toward us show a blue shift relative to the galaxy's average. The parts rotating away show a red shift. By mapping these shifts across the disk, we can construct a rotation curve, a measurement of how fast different parts of the galaxy orbit the center. That rotation curve tells us about the mass distribution, and from the mass distribution, we can infer the dark matter halo that surrounds the visible structure. All of this from light that left Andromeda more than 2.5 million years ago, arriving tonight to be collected by telescopes and analyzed by instruments and processed by the same human minds that, on a clear dark night, can also see it with nothing more than unaided eyes. You do not need a rocket to receive information from Andromeda. You need darkness, patience, and a direction. On a clear autumn night, away from city lights, step outside and let your eyes adjust. Look toward the northeastern sky, toward the constellation Andromeda. Find the star Merak, and near it, the faint elongated smudge. Use averted vision if you need to, looking slightly to the side of the target rather than directly at it, which uses the more sensitive peripheral area of the retina. The smudge will appear, barely there, almost a cloud. What is entering your eye at that moment is this: 1 trillion stars. A disk more than 200,000 light-years across. A supermassive black hole 140 million times the mass of our Sun. A halo of ancient stars extending more than 1 million light-years from the galactic center. Tidal streams and debris from galaxies consumed long ago. The future collision partner of the galaxy you live in. All of this encoded in the faintest smear of photons your eye can detect. Think about the physics of that moment. The photons reaching your eye were emitted from individual stars, from vast clouds of gas lit by newborn stellar clusters, from the diffuse halo populations of stars so old they formed when the universe was young. Each of those photons was emitted, perhaps from a star orbiting deep in Andromeda's spiral arms, and traveled outward in all directions at 186,000 miles per second. Most of them went nowhere useful. Most of them are still crossing the void in the other direction, spreading outward into space on the far side of Andromeda, spreading away from Earth, eventually diluting to nothing against the background of the cosmos. A tiny fraction of them happen to be aimed in exactly this direction, and among those, a fraction so small as to be almost meaningless pointed exactly toward Earth, and among those, an even smaller fraction pointed toward this latitude, this longitude, this moment. And of all of those, enough arrived at your eye, at your specific retina, at your specific moment of looking, to register as a faint smudge. The probability of any single photon completing that journey and arriving at exactly the right place at the right time is so small that it barely qualifies as a number in any conventional sense. And yet, enough of them do it, every clear night, continuously, for the smudge to be visible. The universe placed Andromeda at almost exactly the threshold of naked eye visibility. Not comfortable, not obvious, barely there. It is visible, but only if you look carefully. It is there, but only just. There is something considered about that positioning, even if considering implies intentionality that the universe does not have. At 2,537,000 light-years, Andromeda is visible. At 10 times the distance, it would be completely invisible to the unaided eye. At half the distance, it would be a prominent feature of the night sky, impossible to miss. But at this distance, it is just within reach. A reward for effort. Something you have to actually try to see. And in about 4 billion years, that will change. As Andromeda draws closer, its disk will gradually brighten and expand in the sky. Long before the disks of the two galaxies actually intersect, Andromeda will grow into a visible band of light, occupying a widening arc of the sky that no eye alive today will ever see. And then, over billions of years more, the sky will transform into something that bears no resemblance to the sky you know. The starburst of new star formation will ignite regions of brilliant blue light. Tidal tails will arc overhead. Two galactic cores will be visible simultaneously, converging over millions of years. The constellations of tonight will be gone. The stars that form them will have scattered to new orbits in the gravitational chaos of the merger. New patterns will exist in their place, drawn in stars that have not yet been born. Eventually, Milky Way will settle. The starburst will fade as the gas runs out. The new stars will age. The elliptical remnant will grow quieter as the stellar populations age and the universe continues to expand around it. In the center, 144 million solar masses in a single black hole, the merged remnant of Sagittarius A and M31 star. And the sky around Milky Way will be darker than the sky above us is tonight. Because by that time, dark energy will have carried most of the universe's galaxies beyond the observable horizon. The local group, merged into one giant elliptical, will be largely isolated, an island in an expanding, emptying cosmos, with no light reaching it from the distant clusters that fill our night sky today. The universe will have become a quieter place. The longest-lived stars in the universe, the small red dwarfs, will keep burning for trillions of years, far longer than the current age of the universe. Only when the last of them finally exhausts its fuel on the order of 100 trillion years from now, will the era of starlight truly end. Then, the universe enters what cosmologists call the degenerate era, populated by the cooling remnants of stars, white dwarfs, slowly radiating away the heat they accumulated when they burned, neutron stars, dense remnants of stellar explosions, gradually losing their magnetic fields, black holes, which will themselves eventually evaporate over unimaginably long timescales through a process called Hawking radiation. Milky Way will persist into this quiet era. The merged black hole at its center will be among the longest-lasting objects in the universe. It will lose mass slowly, imperceptibly, over timescales that make the current age of the universe look like a brief opening act. All of this is the future that physics writes for what you can see tonight in the northern sky. That faint smudge near Merak is not just a galaxy. It is a galaxy that will, in the very long run, become the place where whatever descends from this moment in the universe's history will find itself. The Milky Way and Andromeda will not destroy each other. They will become each other. And the light that tells us all of this, the photons that left Andromeda 2.5 million years ago and are arriving tonight, is the same mechanism that allows all of this knowledge to exist. We know the distance because Henrietta Leavitt found the period luminosity relationship and Edwin Hubble applied it. We know the approach velocity because Vesto Slipher measured spectra from a telescope in Arizona. We know the collision is head-on because a team with the Hubble Space Telescope spent years tracking individual stars across the sky. We know the merger timeline from gravitational simulations run on computers. We know what the merger will look like because we can observe the antennae galaxies and other merging pairs throughout the local universe. All of this from one planet. All of this from a species that has existed for a few 100,000 years. All of this from instruments made of metal and glass, pointed at a sky we share with every living thing on Earth. What we have, in the present, is the knowledge of all of this. We know the distance to Andromeda. We know its structure, its star count, the mass of its central black hole, the extent of its stellar halo, the chemical composition of its gas clouds. We know it is approaching at 68 miles per second. We know the merger is roughly 4 billion years away. We know what the merger will look like. We know that no spacecraft we can build will arrive before the merger happens on its own. We know all of this because the light keeps coming. Because photons carry information across 2.5 million light-years, whether or not anything can follow them. Because a species that has been here for a few 100,000 years, on a planet 4.5 billion years old, in a galaxy 12 billion years old, in a universe 13.8 billion years old, figured out how to read the light that has been arriving since long before any of us existed. That is a strange kind of relationship with the universe. Not the relationship of a traveler. The relationship of someone who can see an entire world and never visit it. There is a word for this kind of knowledge. The knowledge of something unreachable. We sometimes call it wonder. But wonder is too easy. Wonder requires no work. What we have when we look at Andromeda is something harder than wonder. It is the product of centuries of effort, of astronomers working in cold observatories, measuring photographic plates by lamplight, spending years on a single question, of mathematicians developing the tools that let us interpret what light tells us, of engineers building telescopes larger and more precise than anything the previous generation thought possible, of institutions funding basic research for no reason except the belief that understanding is valuable in itself. All of that accumulated effort, passed forward from generation to generation across centuries, produced the knowledge that when you look at that faint smudge, you are not looking at a cloud. You are looking at 1 trillion stars, at a collision written into the future of this galaxy, at a merger that will unfold across timescales so long they dwarf everything that has ever happened on Earth. Physics has given us sight and withheld transit. It has made us small enough to stand on a single planet and large enough in mind to reach 2.5 million light years and understand what is there. The boundary is real. Andromeda cannot be reached. That is not a shortcoming of our civilization or a limitation of our imagination. It is the shape of the universe we were born into. And within that shape, within those constraints, everything we know about Andromeda was earned. Every measurement, every calculation, every model came from here, from this one planet. Looking out, catching the light. Tonight, if you get the chance, go outside. Find a dark place away from the city. Let your eyes adjust for 10 minutes. Look toward the northeastern sky. Find that faint smudge near Merak. The light you are seeing left Andromeda more than 2,500,000 years ago. It crossed the intergalactic void. It passed through this galaxy. It passed through this solar system. It entered your atmosphere. It found your eye, specifically on this specific night. And for one moment, what arrives at you is the record of 1 trillion stars in a galaxy 2.5 million light-years away, encoded in a smear of photons barely strong enough to register. It arrived here tonight and found you looking. That is not nothing. That is what the universe arranged for you. Good night.